Quiet down, let's get going. So, next week, Monday review, Tuesday quiz, Wednesday late start, we'll go over the quiz, Thursday Veterans Day Assembly.
Oh.
I'm sorry, I won't see you.
Is that
Yes.
No.
You're going to get dismissed from first period, you'll miss all of second period, and depending on how long it goes, maybe a sliver of third period. We'll see, I'm not promising. Hold on. Hold back the tears that you're going to miss this class. I apologize. Okay, I apologize. But what I'm trying to say is, normally we have a quiz and then a review and a test. It's just, I don't, Mrs. Wolf and I talked, we don't think it's really fair if we were to quiz on Tuesday, review part of Wednesday, not see you Thursday, and then like test on Friday. It just doesn't seem right. You know, it just doesn't seem right. So we feel like this quiz is a good representation of what you need to know for 4 through 4, 6. And then we'll get started with chapter 5. Which is all about triangles. All about triangles. Can I cushion the blow real quick? Do you know that expression? Cushion the blow. Soften the blow. About to fall, it puts up a soft on the floor. Protect it. Are you ready?
No.
There's going to be proofs today.
What?
Okay, there we go. We got it out of the way. No more complaining for the rest of the period. All right, dilations. Don't look too close. All right. No. Dilations are non-rigid motions. Non-rigid motions. Why? Because dilations change size. Right? What are rigid motions? They keep congruence. They retain congruence. So dilations, we learned, are non-rigid motions. So the key idea for today. A similarity transformation has a dilation part to it. Did you hear that word similarity? Is it different than congruence?
Yeah.
Do you hear the difference? Similarity, same shape, different sizes. Congruence, same shape, same size. So a similarity transformation, it may have a translation in it. It may have a rotation in it. It may have a reflection in it. But if it's changing the size, it must have a dilation in it. Make sense? If it's going to change size, it's going to have a dilation. So, similarity transformations preserve angle measure only unless the dilations have a scale factor of 1 or -1. Then they stay the same size. The dilation factors of 1 aren't that exciting. They don't change anything. -1, keep the same size, and they'll change the x's and y sign. Remember that yesterday? If you multiply by -1, x and y, -1, you change its location. I guess, is that idea pretty straightforward to us that similar figures have the same angle measures? Lag today. There we go. If I were to take, this is not going to be very pretty. It's okay. Doesn't really matter. You got this, smart boy. You got this. Dumb word. Yeah, I like it. All right. Do you agree these angles are still the same? Even though the sizes are different of the figures. Can you see that? Angles are the same. Sizes can be different. Angles are the same. All right, let's do a similarity transformation. Similarity transformation. We're going to graph ABC. A is -4, 1. B is -2, -2. And C is -2, 1. Would you guys remind me to go back to the other check-in after this one? Kind of drop down to the right there. The other check-in to the left. It's like explained. Yeah. Okay, we'll go back to that. All right, here we go. We're going to do a translation. and then a dilation. So we're going to slide, and then we're going to dilate. So the x plus 5 and the y plus 1 tells us to move all three of these points right 5, up 1. Here we go. A, right 1, 2, 3, 4, 5, up 1. A prime. And A prime is what? What's the x value?
1.
1. And the y value? 2. B prime. Right. 1, 2, 3, 4, 5, up 1. B prime. 3, 3. You can either count on the graph or you can add 5 to the x and add 1 to the y. Be able to do both. And C prime. Right. 1, 2, 3, 4, 5, up 1. C prime. Was that a rigid motion, what we just did? Yes, we did not change the size. So C prime is at what? 3, 2? We just did the translation. All right. Now the dilation. A double prime. Remember, when we dilate by a factor of, what's that dilation factor here? 2. We just multiply the x times 2 and the y times 2. 2, 4. 1, 2. 1, 2, 3, 4. A double prime. B double prime. Ready? What's B double prime? 6, 6. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. B double prime. C double prime. Did you get 6, 4?
Yeah.
1, 2, 3, 4. C. Come on. Double prime. And if you kind of use the flashlight analogy, you should be able to see that it's growing from the dilation center of 0, 0, right? That's where the flashlight is.
So whenever you do the dilation, why don't you go from the actual translation? And you go from...
Didn't I?
You went from the bottom, not from the actual translation.
Are you calling the green one the translation?
Yeah.
I did go from there.
You did?
Yeah, I took these values and I multiplied by 2. So I got 2 times 1 is 2. 2 times 2 is 4. I didn't go from the original. I didn't go from those ones. You follow me?
Yeah.
What would have happened if I would have accidentally gone from the original? It would have been over here,
Yeah.
right? Make sense? Let's make sure we answer all the questions. Graph the original, its image after the similarity transformation. Now, I guess on the last quiz, I read through the directions and I graphed all 3 parts because on the quiz you guys had original, and then you had a second transformation and then a third transformation. Sorry, 2 transformations, but you had to graph the original also, so I had 3 graphs altogether. I was expecting you guys were going to graph all 3. The directions said graph the image after the composition. So some people just graph the original and graph the final one. And based on those directions, I counted it. I did not mark off for that. But I would be careful. I would definitely graph the translation next and then dilate it. I would graph both. I would just be very careful. All right. Next one. I want you guys to think about this for a minute. No, I promise you I'll go back to the words. The words. Are you ready? Check in. Explain the difference between each pair of vocabulary terms. 1. Congruent figures and similar figures. Who can raise a hand and tell me the difference? Congruent figures and similar figures. Ryan.
Congruent figures like don't change size or like angles, and similar they do change size, like bigger or smaller, like the angle measurements are the same.
Perfect. Well said. 2. Congruence transformations and similarity transformations. What's the difference between congruence transformations and similarity transformations? This one's a little bit trickier. Let me start you out. Congruence transformations involve, what are the, yeah, I like that, because that covers reflections, rotations, and translations. Similarity transformations involve, which one do they have to involve? Dilations. And the last one, which is letter B, I guess it's the second question. Explain why a similarity transformation includes at least one dilation. Because dilations change side lengths, right? Change side lengths. Just kind of a little vocabulary practice. Oh, did that one stop working? And we're back. All right. Take a look at this one. Describe a similarity transformation that maps the trapezoid PQRS to trapezoid WXYZ. Think about it for a second. Talk to your table partner, and we'll report back here in about 30 seconds.
Dilation by how much? Good question. Yeah, that's
All right, let's get back. I heard some good conversations. First thing you would have to do to map PQRS to WXYZ. Now, the thing to be careful about, notice what it says it maps the blue onto the green, because that's going to change what you have to do. So you have to read the directions carefully in the homework and then on a quiz or a test. I guess not a test. We're not taking a test on this. But we're going from blue to green. Who's got an idea? Olivia.
You reflect it over the Y and then you dilate it down.
Dilate it down?
Yeah, like using a fraction.
Let's check that first. So let's see. Here's the y-axis. If we reflect this over the y-axis, P is going to be, let's see, right now it's -6, 1, 2, 3. It's going to be positive 1, 2, 3, 4, 5, 6 over here, 1, 2, 3. Now they didn't want us to actually graph this, which is why we're off the grid. Off the grid. 1, 2, 3, 1, 2, 3. This is where Q prime would be. And I'm not recommending you graph this. I'm just trying to help us visualize it. This is where R prime would be. And then S prime would be somewhere over here. So, can you envision this purple reflection? It's getting us oriented the right way. It's getting pointed the right way now. So I like that. A y-axis reflection. So reflect. Now they use the word reflect in the y-axis. I like the word reflect about. x. And then Olivia, what did you say next?
And you dilate it smaller, you move like a fraction.
A fraction. I hear some other groups say it's going to have a negative dilation factor.
Or to make it smaller, just like change the
Do you think it's negative or do you think it's a proper fraction? Proper fraction. Good. Now, are you ready? The way you can kind of, sometimes students look at this and they get kind of overwhelmed because there's 4 points. They're like, well, how can I make all 4 of those points? If you map one of the points correctly with the correct rule, it should map all the points. So something I do, I kind of look at the letters that are getting matched up. And since I have Q prime on my graphing window here for this problem, I'm going to look at that one. So I'm going to map Q. What should Q get mapped onto? X. Very good. So to map Q onto X, Q is at 1, 2, 3, 1, 2, 3. Technically Q prime. 3, 3. And it's going to get mapped onto 1, 1. How do we find the dilation factor? Old divided by new or new divided by old? Good. So 1 is the new one. Trying to go from this dashed purple one to the new one, green. Agree? So we would take 1 divided by 3 or 3 divided by 1?
1 divided by 3.
1 divided by 3. So dilate P prime Q prime R prime S prime by K equals 1/3. Or you could have said a scale factor of 1/3. Both of those are correct. K equals 1/3. And then you could check the other ones. P is now at, it was at 6, 3, I believe. P prime was at 6, 3. Let's double check it. If we multiply both of those by 1/3, what's 1/3 of 6? 1/3 of 6. 2, 1/3 of 3. 1. 3, 1. Is that right? Did I say 3? No, 2. 2, 1. 2, 1 is correct. Will it work for negatives? Well, R prime is down here at 0, -1, 2, 3. R prime's down here at 0, -3. What's 1/3 of 0? 0. What's 1/3 of -3? -1. 0, -1 is where y ends up. I feel pretty confident with a scale factor of 1/3. New divided by original. New divided by original to get the scale factor. Good with that? Awesome. Now, when you see this proof, it's not really a 2-column proof like we thought about in the past. So don't let this stress you out. All right, we've got a square, ABCD, with a side length of R. We've got a square, EFGH, with side length of S. And AD is, what's that symbol again? Parallel to EH. How do we prove that that square is similar to the other one? Well, it's not on a graph. It's not on a graph, so we can't use scale factors per se. Like, oh, it's a scale factor of 1/3. Because we can't see it on a graph. But there is a property, theorem, that tells us, and I even prepared this for actually. You ready? There is a theorem that says, and I think you would agree with this, if you can use a rigid motion to map ABCD and line up a vertex, if we could show that a translation and then a dilation can map it onto the new one, then we can show they're similar. Isn't that exactly what we just did here? Didn't we just show a translation and then a dilation mapped it onto the new one? And they're similar? Why? Because they had a scale factor. Does that make sense? Can you envision this? Where's the flashlight right now? A, E, they're lined up now, aren't they? points A and E are lined up. That's the flashlight. Can you see it going out like that? Can you see it? So, because these are both squares, what are the angles in both shapes? 90s. Are they the same shape? Yeah, they're both squares. Are they scale factors of one another? Okay. And what would the scale factor be?
It have to be a positive, right? Because it's.
I agree, it's a positive. Where are you getting that from?
I don't know. Yeah,
90, 90, 90, 90.
We know this.
There's 4 90.
we do.
Well, we can figure it out. What's the scale factor between these two squares? Make me proud. Make me proud.
New divided by old.
So
This one, I think this deserves candy. Do you agree, Tessa? Ella, do you agree? You agree with candy?
I agree.
I mean, I got Starbucks. That's
What is
Starbucks.
your candy corn?
It was eaten, like,
What?
not by me.
I don't have any more.
Aren't pink the best? Starburst.
Yes.
Starburst.
No. Yes.
Pink are the best. I'll let you pick between red, pink, and orange. Caden, you got this?
Is it K equals EF over AB?
come on, David.
You're so close. Don't pick those two sides. We don't know their measures.
Oh,
K.
EH over AD, right?
EH.
Wait.
I don't know those sides. What are the two sides they gave us?
AD over EH.
What'd you say, Katie?
R and S.
I don't know those sides. Square ABCD has a side length of R.
Oh.
Square
R and
EFGH has a side length of S. I'm going to let him finish it out because he got us started.
S over R.
S over R.
Good job, Kate.
What's your choice in color?
Oh.
That was greedy, but I like it.
I'm like
All right.
best friend.
Now, does that make you angry? I could see some people that made them angry. They're like, Mr. Westphal, I thought a scale factor was a number. Well, yeah, but do you agree? Whatever S is and whatever R is, you would do S over R. New divided by original. What's up? I didn't hear what you said.
I was only angry that I didn't get the candy.
Oh, gotcha. Not about the math.
No.
Okay.
Yeah.
So, what would our argument be now that we've formed our thoughts? Well, this is more of like what we called a paragraph proof back in the day. If I can type this out, we'll see. Here we go. Here goes nothing. All right. A, B, C, D gets mapped onto E, F, G, H by a translation and then by a dilation of K equals S over R. Therefore, square ABCD is similar to EFGH. So, if you can show a figure gets mapped onto another one with a translation and a dilation, or a reflection and a dilation, doesn't that show that they're similar figures? Because then we found the scale factor that made them similar. Does that make any sense to you guys, just theoretically? Yes, no, maybe? Okay. We were fine with another graph. We just generalized it now. Got that written down? Chase, you got it? Why not? Starburst? Caden got the Starburst.
He's a kind friend.
Caden, you shared. Which one did you keep for yourself? Red. Who got the pink? Jackson. Starbucks. Starbucks is kind of on my mind. My wife usually texts me Friday afternoons and says, "Hey, can you pick up Starbucks on the way home?" Fridays, Starbucks day. Is it Friday? Celebrate the weekend? $20 later.
Don't look at me. I don't got money.
I'm not looking at you.
All right. We decided I'm not going to put one of these on the quiz for 4. So you guys are going to say, "Oh, he never told us that." And I'm saying it. Not on the quiz. This is not on the quiz.
Is this on the quiz? Just on the quiz.
Who's listening to what he said?
Yeah.
I've said it twice. Yes, McKenna.
Are we gonna have to do like anything similar like the paragraph first?
Similar. I see what you did there. Similar.
Are we gonna
Paragraph proof?
Yeah, do it.
There's no proofs on this quiz. All right, we're going to hold off on that one for now. There's that one triangle one that if you want to try it right now, you're welcome to. But you can start the homework. Get a healthy start. We got 7 minutes, Levi. We got 7 minutes to start this homework.
He's not gonna do it until
Science.